We will now illustrate a transient analysis by simulating a rapid drawdown case. To start with, we have the long-term steady-state condition here, and we are going to take away the reservoir by drawing down the reservoir. And we are going to look at two cases, one where the reservoir is drawn down completely, and the assumption is that this happens instantaneously. In the second case, we're going to draw the reservoir down over a period of 5 days. So in the second case, our boundary condition is going to be a function of time. In the first analysis, the boundary condition will be a constant, but the dissipation of the excess pore pressure that is in the dam will take some time. We are going to use a sample function for silty clay, and we're going to make the saturated volumetric water content 0.4. We are going to work in terms of meters per day in this particular case. We're going to use the Van G estimation technique for the conductivity function, and we are going to use a residual water content of 0.05, and we are going to convert the conductivity in meters per day. 8.64 times 10 to the minus 2 meters per day is equivalent to 1 times 10 to the minus 5 centimeters per second, I believe. So we're going to create several analyses. We have to start with a steady state analysis to establish our initial conditions, and then we are going to do an instantaneous drawdown, and the reservoir will drop from 8 meters to 0 meters instantaneously. Then for the second case, we're going to do a slow drawdown, and the reservoir will be drawn down over a period of 5 days, which means that we will have to create a boundary function. And in both cases, we are going to look at the factor of safety versus time by using the SEEP results in slope W, and the added feature here is illustrating how the SEEP results are used in slope W. So in the end, we will have an analysis tree that looks something like this, and we will create this analysis tree and talk about it as we create the analysis tree. And for illustrative purposes, we are going to do a transient analysis for 30 days. And we are going to have a time step sequence that's exponential, and we are going to have a total of 10 time steps, and the first time step is going to be a quarter of a day. We will demonstrate how the transient analysis gets its initial conditions from a previous analysis. And then here is our boundary function that we are going to create, how the reservoir is drawn down from 8 meters down to 0 meters over a period of 5 days. And then finally, we'll take a look at the change in the contour of zero pore water pressure with time. Let us then go to GeoStudio and open up SEEP 12. And there is one analysis already flagged. In the analysis tree, we have one analysis. Notice that the analysis type is a steady state analysis type. So we are going to do a steady state analysis to set up our initial conditions for the transient case. To begin then, we do not have any materials, so that we can create our material to represent the dam with draw materials. We have a tow drain, and the tow drain we know will remain saturated at all times, and it has a very high conductivity of 1 meter per second. We do, however, have no material for the embankment itself, so we can say key in, add a material, and let's call this embankment. We will use a saturated, unsaturated material model, and we'll use our traditional light yellow color for the embankment. Now we need a volumetric water content because we anticipate that we are going to do a transient analysis. Also, we want to estimate the hydraulic conductivity from the volumetric water content function. We, however, have no volumetric water content function, and so we can click on this button here, ... and we can create a volumetric water content function, and we were going to call this silty clay. The type is a data point function. We estimate the function from a sample function from silty clay. Silty clay from the drop-down list. Our saturated water content we said was going to be 0.4, and we are going to accept the default for the suction range for the estimated water content function. And we should look at it in terms of a log scale. We can do this with the edit points case. While we are here, I want to demonstrate to you and for you how we enter an m sub v value. We can enter a constant here, say 1e minus 4 1 over kPa. Now, how do we know what the significance of this is? That we can uncheck use auto scale, we can view the function, and we can look at the function over, say, minus 20 to plus 20, a specified range. And notice now how we can see the slope. We can see the slope here that represents m sub v. This is the slope m sub v. And then we have a very high air entry value, and it goes down onto the function. It is always good practice that when you are going to make use of an m sub v value, that you take a look at your function close to zero pressure and ensure that the m sub v slope is nice and continuous with the volumetric water content function. Going back then to the auto scale and looking at it in terms of a log scale, here's our volumetric water content function for the silty clay. Close. Now please remember that it is once we have defined the function, we always have to associate it with the material. A very, very important step. We always have to associate the function with the material. Now we need a hydraulic conductivity function. We once again can click on the ... button. We can add and say this is the silty clay conductivity. And again, we are going to use a data point function, and we are going to estimate the function from the water content function we had just established using the Venn method. And we can now select our silty clay volumetric water content function, and we said that the saturated conductivity was 8.64 E minus 2 meters per second, and we had said that the residual water content was going to be 0.05. And when we click on OK, and once again click on the Edit Data Points, here is our silty clay conductivity. Closing this dialog box then, again, it's very important now that we have defined the function that we associated with the material. So now we have an embankment material, we have a volumetric water content function, and we have a hydraulic conductivity function. Now we can associate the material with the regions. Notice that we have already in the past defined a boundary condition on the upstream face. You can check as to what it is with View, Object Information. If you click on this line, it is a hydraulic boundary condition with a total head of 8. So there is just another feature for you to check as to what has been defined. We need to define the boundary condition for the tow drain. We know that the total head everywhere in the tow drain will be the elevation 0. I believe a boundary condition has already been defined. Draw boundary conditions, and we have a tow drain boundary condition. The tow drain boundary condition is a total head of 0. I'm going to change the color of the total head boundary condition to say a green so that it will be more visible, and we can then apply. Notice that what I'm now going to do is I'm going to apply the boundary condition to a region. Applying the boundary condition to a region, because we know the total head everywhere in the tow drain is a total head of 0. Now, I believe that we have completed the definition for the long-term steady-state case. We have our geometry, and we have our materials, and we have our boundary conditions. Clicking on Verify, we see there are no errors and no warnings, saying that there is sufficient data for us to make some calculations. Clicking on the Solve button and clicking on Start. And then looking at the results view, we are back to where we were in our session 1, where we did a steady state analysis for this particular case. I'm going to turn off my flow vectors, turn off my boundary conditions, and so here is my solution for the long-term steady state. Now I want to simulate removing the reservoir instantaneously. We can now go back to the Define view. Under Key in Analyses, we are going to say we want to do something on this cross-section. It's very similar, but there are some minor changes. Number 1, we are going to clone this steady state analysis, and we are going to call it number 2, say instantaneous. Drawdown. Tabbing out of this box, we notice that this changes. In order to keep our analyses in somewhat logical order, it is always useful to number them. So go back and renumber the initial steady state, making it 1, so that it appears higher up in the tree. And if we're going to rename it, then we have to recalculate it, but that's okay. Now, the instantaneous drawdown should be a transient analysis. The analysis type must be transient. So we select a transient analysis. And then where are we going to get our initial pore pressures from? We have to say as to where are we going to get the initial pore pressures from. In this case, we want to get the initial pore pressures from our parent, from the parent. And who is the parent? The parent is the initial steady state. So 2 steps. We have to say, where will the pore pressure come from the parent, and then we have to identify the parent. And notice immediately when we have a dependency, number 2 is getting some information from number 1. So number 2 is a child of the parent number 1 in this particular case. The next step is to simulate the define the boundary condition which infers that the reservoir has been removed. We go draw boundary conditions, remove from a line the upstream boundary condition, and now we want to assign a new boundary condition, but we only have 2, so we need a new boundary condition, and there are several ways of doing this, but I'm going to do it a more methodical way by saying add and draw down level, and the drawdown level will be at elevation 0, so we can specify a total head with an action of 0. So close. Now we're going to draw this on a point. Say point, drawing the drawdown boundary condition on the point. Notice that when my cursor comes close to a point that the cursor changes, and so I'm going to apply my boundary condition here. Now, when we were here, and we're now going to draw the water table down, but there still may be a seepage phase here. And we don't know where the seepage phase is. And we don't know to what extent. Obviously, the size of the seepage phase will change with time as the water dissipates from the embankment. So we need to apply a potential seepage phase where the reservoir was. Once again, draw boundary conditions. We don't have a boundary condition of that type, so we can go directly to the key in boundary conditions dialog box. We say add, and this would be the upstream face. And in this particular case, if you recall from session 1, it needs to be a flux boundary condition, but we need to flag on this particular checkbox here to indicate to SEEP-W that a potential seepage phase could form on the upstream face. And the blue color is probably quite appropriate, and so we say draw, but this time we want to draw the boundary condition on a line. Once again, as I noted in session 1, the hollow triangles indicate to you that the flag potential seepage face review has been turned on. Now recall, we are doing a transient analysis, so we need a fourth feature in a transient analysis. Recall that it's geometry, material properties, and boundary conditions. We've done those three things, but now we need to say something about a time-stepping sequence. So we go to the Key in Analysis dialog box, and we have a tab here called Time. And we are going to click on this tab and set up our time-stepping sequence. We said that we were going to run this analysis for 30 days. We were going to have 10 time steps, and it was going to be exponential, and the first time step would be 0.25 days. And so you can see that our total elapsed time here, our total elapsed time is 30. Our first delta t is 1/4 of a day, and in the end we are going to run an elapsed time of 6 hours, 1 day, 2 day, 3 day, and so forth. So to repeat, we have the 4 elements of a transient finite element analysis. Clicking on verify, we have 0 errors, 0 warnings. We should now be able to analyze this particular case. Clicking on the solve, saving the problem, clicking on start, and I get an error message, and the reason is that I renamed my steady state analysis. Consequently, there is no solution, and so the transient cannot run because there is no solution for the initial conditions. So I need to select both of these and run them both at the same time. And now it goes through the steady state analysis again, and then through the transient analysis. Once again, there's a lot of information that goes by in the solve window, but what you do note is there are time steps. And in each time step there is a seepage face review, time step 9, time step 8, 7, and so forth. Now generally we don't look at this too carefully, but sometimes it is useful to go back and see what has transpired here. Now we can go back and look at the results. And notice now that we are looking at the pore pressure distribution on day 30, after 30 days. We can now step through all the time steps. Here's where we started from before the reservoir was drawn down. If this edit box has the focus, we can use the down arrow key and step through all the times. And we see that in this case the reservoir was drawn down instantaneously, but notice the large seepage face that still has developed, particularly at the quarter day. If we turn on our flow vectors, notice how the flow that is coming out of the upstream face, and that the pore water pressure is 0 over a large portion of what was in contact with the reservoir. Taking away the arrows again, we can now step through all the time steps and watch how the excess pore pressure dissipates as we reach the end of 30 days. So here we are at the end of 30 days. Another rather useful and interesting piece of information is note how at day 1 that the flow dissipates out of the embankment in this direction, but at this stage there is still some flow that dissipates out of the embankment in this direction as well. Another view that is often quite interesting and useful is to take a look at how does the contour of zero pressure or water table or piezometric line, whatever you like, how does it change with time? We can do this with the command called draw isolines. Isolines are a contour of a certain value at various times. In this particular case, we want to draw the pore water pressure, which is 0, representing the piezometric line, and we want to draw it for all time, and we want to select all the time, and when we click on apply, we see that we have the position of the zero pressure contour line at various times. If I now go back to my time edit box here, and this is the initial condition, notice that the current time is the one that is dashed. So you can tell from this edit box as to by the dashed line at which time each of these contours are represented by. Alternatively, you can actually label these contours by saying draw contour labels, and we can click on the contours and we can see where the position is of the zero pressure line at various times. Once again, we can click on flux labels or contour labels and make the font a little bigger so that we can see the labels more clearly. Once again, to remove a label, just click on an existing label and they disappear. Now we will use these transient seepage results in a slope stability analysis. We will compute the factor of safety for each of the time steps that we saved pore pressure results. So we go back to the define view, and under the analysis tree, key in analysis dialog box, we say add a slope W analysis limit equilibrium. We are going to select a Spencer type of analysis. We'll rename this stability analysis as fast stability, fast drawdown. We are again going to get our pore water pressures from the parent, and the parent is the instantaneous SEEP-W analysis. Now, one other thing that is extremely important is that we want to now compute the factor of safety for each one of these 10 time steps. We could select any one day and compute the factor of safety, but in this particular case, what we want to do is we want to select all of the time steps. So we have selected all here. And this means that slope W will do 10 different stability analysis with 10 different pore water pressure distributions. In our slip surface, we want to look at the upstream face, so we now need to go right to left, and we will use the enter-exit approach to specifying trial slip surfaces. Note we are now in a stability analysis. The regions have a gray color. That means the material has not been assigned yet to the regions for a slope W analysis. We say draw materials, and we notice that we have an embankment material, but the properties have yet not been defined for this material. We will select a more Coulomb strength envelope. The unit weight is 20 kilonewtons per meter cubed. The cohesion is 5 kPa, and the friction angle is 27 degrees. Now we can assign this material to the regions. We must now define our enter-exit ranges. Draw, slip surface, enter-exit. All slip surfaces will exit somewhere in this area here, and the slip surfaces will enter on the crest. In this particular case, for illustrative purposes, I'm going to refine these numbers, saying that the slip surface should start at an elevation of 0 and end at an elevation of 5, and I want 10 increments at the exit point. At the crest, I will go from one edge of the crest to the other, which is 23 meters and 27 meters. And I will have 5 increments, and I will have 10 radii. When we click on apply, we notice that the enter and exit ranges are adjusted accordingly. So now we can compute the factor of safety and how it changes with time after the drawdown. Clicking on verify, we have 0 errors, 0 warnings. Clicking on solve, and just to be certain, let us select all the analysis and reanalyze all the cases. And now for the stability analysis. We have done 10 different stability analysis. Going to the results view, we notice here that we can look at the factor of safety at any one of the times for which we've done an analysis. This was 6 hours, increasing the font of the factor of safety so we can readily see it. This is now the factor of safety 6 hours after instantaneous drawdown. Once again, if this edit box has the focus, we can use the down arrow key, and notice as the pore pressure dissipates, the factor of safety goes up. So in this particular case, the factor of safety is obviously the lowest because we have somehow magically removed the reservoir instantaneously. And as the pore pressures dissipate, the excess pore pressures, the factor of safety goes up. Now there is another way to look at this result, and that's say draw slip surfaces, and we have here an option say draw slip surfaces, and we have an option here to plot factor of safety versus time. When we click on the graph button, we see this graph, say set options, remove the legend. It's kind of meaningless in this particular case. And we see now that the factor of safety, of course, was very low, be less than 1, if we were to draw the reservoir down instantaneously, but the factor of safety increases as the pore water pressures dissipate. Now let us go back to the define view, once again to the key in analysis dialog box. And so now we want to repeat the instantaneous drawdown problem. The problem will be very, very similar, except that we want to draw the reservoir down slowly over a period of 5 days. So highlighting analysis number 2, we can clone this analysis because the setup is going to be very similar. Let's call this analysis number 3, slow drawdown. Once again, our starting conditions will be the initial steady state condition. Our pore pressures again are going to come from the parent analysis. The only thing that we are going to change is the upstream boundary condition. So we now have a transient analysis again, and we now need to change the upstream boundary condition to represent the drawdown with time. Starting with draw boundary conditions. First of all, let's remove this old boundary condition from the line and remove this point boundary condition. Now we want to create a new boundary condition, key in. We add a new boundary condition, call it slow drawdown. And in this particular case, we want to select that the boundary condition is a function. So we select function. We don't have any functions, so we need to define a function, and we need to add a function, call it drawdown curve. And it will be a head versus time type boundary function, and the boundary function will be a data point function. And at time 0, the head will be 8 meters. At time 5 days, the head will be 0. So here is our drawdown curve. Now it is useful to recognize that if we are at a time greater than 5 days, the head that is used is the last data point. We can see what the function looks like at past 5 days by looking at the graph from 0 to 30 days, for example. And notice that the drawdown now comes to 0, but after 30 days the function remains constant at 0. So now we can select our drawdown function, and we'll select a different color, say orange, and close, and we can now assign the slow drawdown function to the upstream face, the region edge. Now the circles are solid, so I forgot to do something, and that is that I have to turn on my potential seepage face review. Going back to the function for the slow drawdown boundary condition, I should have checked potential seepage face review. this needs to be checked here. Notice now how the circles are hollow, indicating once again that it is a sign that we will do a potential seepage phase review as part of the solution. Clicking on Verify, we have 0 errors, 0 warnings. We should have enough information to make a calculation, saving the result. And we want to do the slow drawdown analysis now. And now if we go to the results view, and once again we click on 0, here is our initial condition, which was our steady state solution. At the end of 6 hours, the reservoir has not been drawn down very much. And then notice how the reservoir at day 1, day 2, day 3, and day 4, the reservoir has been drawn almost completely down, and then by day 6, it's been drawn down to its maximum level. But notice how the piezometric line continues to decrease, representing a further decrease in excess pore water pressures. Now going back to the define view, we want to repeat our stability analysis where the reservoir is drawn down slowly. So once again we click or highlight the stability analysis, and we want to clone the stability analysis, and we will rename it slow stability, slow drawdown. And we must now say that our pore water pressures come from the parent, but now the parent is the slow drawdown SEEP-W analysis. And so once again it's indented under the SEEP-W analysis. Other than that, notice that the stability analysis is identical. We are right to left, enter, exit. Our pore water pressures come from the parent analysis, and we are going to do it for all 10 time steps for which we have saved data. So here's our stability analysis. Everything is the same as before, except that we have different pore water pressures. Now we can rerun the stability analysis. Close, going to the results view, starting again at 6 hours. The reservoir has been drawn down a little bit, but notice the stabilizing effect of the reservoir. After 6 hours, our factor of safety is still quite high. But then as the reservoir is taken away, the factor of safety falls and continues to fall. But then as soon as the reservoir is gone, then the factor of safety goes back up as the pore water pressure dissipates. Once again, looking at draw, slip surfaces, factor of safety versus time. Once again, we don't need our legend here. And we can look at it at a bigger font. And so we see now the factor of safety was very high under static conditions. Then with the slow reservoir drawdown, the factor of safety diminishes. But then after the reservoir is gone, when the pore pressure dissipates, the factor of safety again increases. This is one of the powers of the GeoStudio integration, how that a transient seepage analysis can be used in SLOPE-W to look at factor of safety versus time. This brings us to the end of this illustrative example of a rapid drawdown type of analysis where the reservoir is drawn down instantaneously or where the reservoir is drawn down over time. And this is an illustration of a transient case and how we have used the transient SEEP W results in a slope W stability analysis. Going back to our proceedings or PowerPoint presentation then, here is just another view of how you might view the results at the end of a particular time. And this is the graph that we have already looked at, just to point out that this feature of factor of safety versus time was added in version 7.1. If you have an earlier version of version 7, then you will not be able to make this graph, but upgrades to the latest version once you have version 7 are of course free, and you can readily upgrade to the latest version and produce this type of graph. And this is probably the more interesting graph in that how the reservoir is drawn down with time. The factor of safety does not fall nearly as low. In fact, it never falls below 1. And I would submit to you that this is a much, much more realistic case than the instantaneous drawdown case. This then brings us to the end of this illustrative example.